So this is a slightly modified version of the previous problem. X and y again are distributed according to the density function 6x, which is defined over some shaded region shown in the figure. But instead, now z, a new random variable, is defined as x plus y. And again, we are required to find the probability density function of z, which is fz of z. So if we start with the distribution function approach, that means computing f capital Z of z. It is by definition the probability that the variable z is less than small z. And in this case, the variable z is x plus y, and it has to be smaller than small z. So rearranging this tells you that this is the probability y less than z minus x. So to compute the distribution function, we need the probability that y is less than z minus x. And to do that, let's go to the figure and see where y equals to z minus x for arbitrary values of z. So obviously, because it's minus x, that means the line is of unit negative slope, but z is the intercept. So if z is below 0, then the line z minus x will look like this. And if z is between 0 and 1, the line y is equals to z minus x will look like this, where these intercepts are z and z. And if z is between 1 and 2, the line will be like this, z minus x, and x is z is between 1 and 2. And we are required to find the probability that y is smaller than z minus x. That means that we look below these lines and see where the density really is between x and y. So looking at this line, when z is negative, if we look below this line, there is no density of x and y, so this case is really trivial. If we look at this case, when z is between 0 and 1, the probability that y is less than z minus x means that we look below this line and we have some region where the density is defined. The other case is when z is between 1 and 2, and for that case we have another region where y is less than z minus x. So let's call these cases as case 1 and case 2 and investigate them separately. That means for each case we will find this first, and then we take derivative to find the density function. So let's start with case 1, where z is between 0 and 1. So let's draw the figure again. So this is x, this is y. This is the region where the density is defined. And y equals to z minus x in this case looks like this. And the region where y is less than z minus x is actually this region. So the shaded region is where y is less than z minus x, and that region overlaps with the density here. So what this means is we need to integrate the density over this shaded region. So for this case, fz of z will be the integral of the density The density in this case is 6x. Integrating over this region, it's easier to do dy first and then dx. Okay, so when we do dy, that means we need to figure out what y is at the lower limit and then what y is at the upper limit, because this line here is y equals to x. The lower limit will be x. The upper limit is defined by this line where y is z minus x, so this will be z minus x. And for x, the limits of x goes from 0 from this point here all the way up to this intersecting point. And if we find the intersection between this line here and this line here, we'll figure out that x will be z over 2. So the limits for x are 0 to z over 2. So now we just need to compute this integration. That turns out to be 0 to z over 2, 6x times z minus 2x dx. So this will be 3z x squared minus 12x cubed over 3 from 0 to z over 2, which turns out to be 3z times z squared over 4 minus 4 times z cubed over 8, and this turns out to be 3z cubed or 6 z cubed minus 4z cubed, which will be z cubed over 4. So the density function is just the derivative of this, so that will be d over dz times fz of z. So the derivative of this will be 3 over 4z squared, and z was between 0 and 1. So we've obtained the first part of the solution. For the next part, that means the case number 2. So let me erase this part here. This is no longer required. We have finished case 1. So case 2 is this one where z is between 1 and 2. So for this case, fz of z, which was the probability that y is smaller than z minus x, means we need to integrate over this region here. But notice that this region here is not triangular, so it's harder to integrate over this region. So what we do instead is we integrate over this region and subtract it from 1. So that will mean we will say 1 minus the integral over this smaller piece of the smaller triangular piece. So again, it will be 6x. This time we will do dx dy, and the limits, because we are doing dx, so we need to figure out what x here is and what x here is. X here should be is defined by this line, so it will be z minus y. X here will be simply y. So this will be z minus y to y, and y will be from this point here all the way to 1, and this point, as we figured out, was y equals to z over 2. So it will be from z over 2 to 1. And computation again is the same, 1 to z over 2. It will be 3x squared from z minus y to y, and then dy, which will be 1 minus z over 2 to 1, 3 times y squared minus z squared minus 2zy minus y squared dy, which will be 1 minus, so this y squared and y squared cancel, so we'll be left with 1 minus, so 3 can stay outside, so this will be minus z squared y minus 2z y squared over 2, so this 2 to cancel, the limits are z over 2 to 1. So this turns out to be 1 minus 3 times minus z squared minus z minus z squared times z over 2 minus z times z squared over 4. So this will be 1 minus 3 minus z squared minus z plus z cubed over 2 plus z cubed over 4. And the rest is just differentiating this with respect to z to obtain the density function. So then fz of z will be the derivative of this. The derivative is minus 3 minus 2z minus 1 plus 3 over 2z squared plus 3 over 4 z squared, which turns out to be 3 times 2z plus 1 minus 9 over 4z squared, and when z is from 1 to 2. So there we are. We've obtained the density function of z, and this density function is in two parts. One is when z is between 0 and 1, the density is 3 over 4 z squared, and when z is between 1 and 2, this is the density function here.